Hi, this is Sai Potana, founder at Embeddedsystems.ai LLC. In this video, I'm going to talk about the most widely used low to medium speed communication buses used across embedded systems, automotive electronics, industrial control, IoT devices, and consumer electronics. Each bus was designed for a different purpose. Some prioritize simplicity and low cost, while others prioritize reliability, deterministic timing, or higher throughput. We'll talk through each protocol, explain its architecture, signaling method, speed, topology, and real-world applications. Section 1 shows I2C inter-integrated circuit. It is one of the simplest and most popular chip-to-chip communication buses. I2C uses only two wires, SDA for data, SCL for clock. It uses an open drain shared bus architecture with pull-up registers. A single master can communicate with multiple slave devices using addresses. Typical speeds range from 100 kilobits per second to about 3.4 megabits per second. I2C is extremely common in sensors, EEPROMs, RTCs, power management ICs, low-speed peripherals. Its major advantage is simplicity and minimal wiring. Its limitation is relatively low speed and short PCB distance. Section 2 talks about SPI, Serial Peripheral Interface. SPI is designed for much higher speed communications compared to I2C. It uses four signals primarily: MASI, MISO, S-clock, chip select. Unlike I2C, SPI is full duplex and push-pull driven, allowing much faster transfers. Typical speeds are 1 to 10 Mbps, sometimes much higher on modern MCUs. SPI is commonly used for flash memory, displays, ADCs, and DACs, high-speed sensors. The downside is increased pin count because each slave generally requires its own chip select line. Section 3 describes LIN, Local Interconnect Network. LIN was developed specifically for low-cost automotive electronics. It's a single-wire serial bus based on UART signaling. LIN uses one master and multiple slaves. Typical speeds are below 20 kilobits per second. LIN is ideal for non-critical automotive systems such as seat controls, mirrors, window motors, lighting modules. Its primary advantage is very low implementation cost. However, it is not suitable for high-speed or safety-critical communications. Section 4 describes CAN, Controller Area Network. CAN revolutionized automotive networking. It uses a differential two-wire signaling system, CAN high, CAN low. Differential signaling provides excellent noise immunity and long-distance reliability. CAN supports multi-master arbitrations, message prioritization, fault detection, automatic retransmissions. Typical speeds are between 125 kilobits per second to 1 Mbps depending on cable length. CAN became the backbone of automotive electronics including engine control, braking system, powertrain, industrial automation. Its deterministic arbitration mechanism made it highly reliable for real-time embedded systems. Section 5 describes CAN-FD, CAN with flexible data rate. CAN-FD extends classical CAN. The arbitration phase still runs at standard CAN speed, but the data phase can run significantly faster. Typical data phase speeds are 2 to 5 Mbps, sometimes higher. CAN-FD supports larger payload sizes, higher throughput, backward compatibility with CAN. This makes it highly suitable for modern vehicles with increasing sensor and ECU data demands. Section 6 describes FlexRay. FlexRay was developed for safety-critical automotive systems requiring deterministic timing. Unlike CAN's event-driven arbitration, FlexRay supports time-triggered communication. It uses dual differential channels, fault-tolerant operation, deterministic scheduling. Speeds reach up to 10 Mbps. FlexRay is used in drive-by-wire, steer-by-wire, chassis control, advanced safety systems. Although powerful, FlexRay is more complex and expensive than CAN, which limited its widespread adoption. Section 7 talks about UART, Universal Asynchronous Receiver Transmitter. UART is one of the oldest and simplest serial communication methods. It uses TX and RX. No shared clock exists between devices. Instead, both ends agree on a baud rate. UART is point-to-point communication that is used for debugging, bootloaders, module communication, diagnostics. Common baud rates include 9600, 115200, and higher. Its simplicity makes it universal across embedded systems. Section 8 talks about CENT, Single Edge Nibble Transmission. CENT is a specialized automotive sensor communication protocol. It uses a single wire and transmits data using pulse timing rather than traditional clocked serial communication. CENT is commonly used for pressure sensors, throttle sensors, temperature sensors. Its advantages include low cost, strong EMC performance, simple wiring. It became popular in automotive sensor interfaces where analog signals were replaced with digital sensing. Looking across all these buses, I2C prioritizes simplicity. SPI prioritizes speed. LIN prioritizes cost. CAN prioritizes robustness. FlexRay prioritizes deterministic safety. UART prioritizes universality. CENT prioritizes sensor efficiency. Each protocol exists because embedded systems require different trade-offs between bandwidth, reliability, complexity, latency, cost, and wiring overhead. Modern vehicles and embedded systems increasingly combine multiple buses simultaneously. For example, LIN handles low-cost actuators. CAN or CAN-FD handles control systems. FlexRay handles deterministic safety systems. Ethernet increasingly handles high-bandwidth ADAS and AI data. Rather than replacing one another, these buses form hierarchical communication architectures. Understanding these buses is foundational for embedded firmware engineering, automotive electronics, robotics, industrial automation, IoT systems, hardware bring-up, and diagnostics. Each protocol reflects an engineering balance between performance, cost, determinism, and system complexity. Together, they form the nervous system of modern electronic systems. Thank you.